All right, I believe this is problem number 10, and we're asking which one of these is true. Now, there's a couple different ways you could have gotten to the answer here. Number one, if you look at Professor Wong's notes, he does explicitly say that R is not countable, and if you know that that is true, then therefore the other things are not going to be true. The next thing you can do is process of elimination. So we need to start by defining, okay, what is, this symbol Z, my handwriting is not very good, but it's it's a Z. And so that's going to be, everything up to -3, -2, -1, 0, then 1, 2, and then we just keep going until infinity. So it's going to be, to negative infinity and to positive infinity. Then we also have this R. R is the set of all real numbers. So real numbers includes all of the natural numbers. It includes all of these integers. It also includes all rational numbers that are made as fractions, like, 0.5. And then it also includes any decimal that kind of goes to infinite places, like, for example, pi is not a rational number because, it has an infinite number of, decimal places. But it is part of the set of real numbers. The next thing we want to do is kind of determine what we mean by countable, denumerable, what is enumerable. Essentially, enumerable and countable, I think we can just kind of consider that as a synonym. There are some slight differences, but I think that's beyond the scope of what you need to know for this course anyway. But when we say enumerable, we can kind of just think of it as, countable. But then when we say denumerable, it actually kind of means the same thing. You might think it's like the opposite, but actually it would be countable, but it's also countable and infinite. And another way to define, denumerable, we could say, for example, that the set of all integers is considered to be denumerable if and only if the size, the cardinality of the set of real numbers is equal to the size of the natural numbers. So let's try to get an example of that. This is actually a pretty easy set to work with, so we'll go ahead and do that. We want to prove that this set is denumerable, or that it is countable, or that it is, at least not any bigger than the size of natural numbers. And we could prove that it's countable by taking the natural numbers, right? The natural numbers are, actually they start at 0, 1, 2, 3, 4, 5, 6, and so forth. And we have this set down here, we're just going to call it A. And we are going to write that out real quick. And we can prove that it's enumerable just by saying that we have some kind of bijection here where we're saying that we can map each one of these numbers to each one of these other numbers here. So we can map 0 to 1, we can map 1 to 3, we can map 2 to 5, we can map 3 to 7, 4 to 9, etc. And as such, if we want to map, something from the natural numbers to A, we can just say, f of x is going to be equal to 2x plus 1. Because all we need to do to figure out which element it is, for example, if we wanted to figure out what 7 maps to, we actually don't see it here. This 6 maps to 13, we don't know what comes next. Well, we can just plug it into the formula here. We got 7 times 2 is 14 plus 1, that is going to be 15. So this maps to 15. And likewise, we can, do the inverse operation in order to map from A back to N. And that is essentially what it means to be countable. So again, these are all kind of asking the same thing. I mean, denumerable, again, remember, it just means that it's countable and infinite. And any subset of a denumerable set is going to be countable. So in essence, all we really need to prove is that, the set of integers is denumerable, and that will, cancel out both of these. So here we have the natural numbers 0, 1, 2, 3, 4, 5, all the way up to infinity. And then here we've rewritten the set of integers, but we're writing them in a slightly different way. Rather than go 0, 1, 2, 3, we're just going to keep going back and forth where we go 0, -1, 0, +1, 0, -2. That way we make sure that everything is being counted. And that's the kind of counterintuitive, kind of mind-blowing thing about this, is that even though we have the countable numbers, which ranges from 0 all the way up to positive infinity, and then you have the integers, which range from negative infinity all the way up to positive infinity, they're actually the same size. And we know that because simply we can map this one to this one, this one to this one, this one to this one, and this one to this one, and so forth. And all we have to do to map n to z is basically say if it's an even number, we're just going to take x divided by 2 if even. So whenever we have, our 0, that divided by 2, that's going to be 0. 2 divided by 2, that's going to be a 1. 4 divided by 2 is going to be 2. 6 divided by 2 is going to be 3, and so forth. And then if it's an odd number, then we just do x plus 1 divided by 2, and then just take the negative of that. And you see we can plug in any number. For example, if we want to figure out what 5 maps to, we just do 5 plus 1, that's going to be 6 divided by 2, that's 3, negative 3. That is what we have. I forgot to write my negative sign here, but hopefully you got that. So therefore, this is a proof that z is denumerable. So we know that this is not true, and we know that this is not true. And we already proved earlier that this is not true. So by process of elimination, we can see that r is not countable. Now, on top of that, there's also a proof, and I'm not going to go over it. This guy, Dr. Payam on YouTube, has an amazing video talking about the proof behind why r is uncountable.